Okay, today we're going to talk about section, you can't really see it, it's section 3.7, which covers indeterminate limit forms and something called L'Hopital's rule. L'Hopital's rule is a really beautiful theorem. Unfortunately, for many students of calculus, L'Hopital's rule becomes this kind of sledgehammer by which you try to attack everything that you see. So hence we have the sledgehammer breaking up the concrete blocks. So it's a tool, right? But with power comes responsibility. And so we want to see what it can do, but also the implications of using such a rule like this. Okay, so we're going to look at the indeterminate limit forms. That is, limits where the expression is a quotient of limits where the numerator and denominator both go to 0, or quotients where the numerator and denominator both go to infinity, or differences where you're trying to subtract infinities, multiply a 0 times an infinity, or take an indeterminate power such as 0 to the 0, infinity to the 0, and 1 to the infinity. So all of those limits are things you can't do straight up. You need some kind of extra machinery, and L'Hopital's rule is one way to solve those. Okay, so just to set up the problem, remember what we learned about limits way back in chapter 2. We learned that limits behave well with respect to arithmetic. So if I have two functions, and I want to find the limit of the sum of those two functions, if those two functions individually have a limit, then I can add the limits of those two individual functions. To put it succinctly, the limit of a sum of functions is the sum of the limits of the function. The limit of a difference of two functions is the difference of the limits of those two functions. The limit of a product is the product of the limits. And all these mean is that you can distribute limits across arithmetic operations and just compute it as you normally would. The limit of a quotient is the quotient of the limits, except for this one special case where you cannot use it to divide by 0. Right? The limit law for quotients comes with a caveat that you cannot use it if the denominator has a limit of 0. Okay. Now, what this doesn't mean is that the limit of the quotient is definitely, it doesn't exist if the denominator goes to 0, but there are special cases which have to be examined. We know that we can't divide by 0. Most of the time, if you have a quotient where the numerator goes to some finite non-zero limit and the denominator goes to a limit of 0, then, again, most of the time, the quotient will be some kind of infinity. As an example, the limit as x goes to 0 from the right-hand side of 1 over x, that's positive infinity. That's basically our motivating example for infinite limits. As x gets smaller and smaller but remains positive, 1 over x gets larger and larger and is positive. So, and the limit is infinity. Or you could go from the left-hand side as x goes to 0 from the left, cosine x over x cubed. As x gets very, very small, this is close to 1. As x gets very, very small, this is small and negative. So the quotient will be large and negative. Therefore, the limit is minus infinity. Okay, now we can't say anything about the limit as x goes to 0 because it's positive infinity from one side and negative infinity from the other side. The only thing you can say is that it doesn't exist. I suppose you could say it's infinite, but it's not plus infinity or minus infinity. Okay. However, it's not necessarily true that if the numerator goes to something non-zero and the denominator goes to something 0, then the limit of that function is infinite. The example that I talked about maybe a month ago was this function here, f of x is 1 over x sine x. So another way to write that would be x times cosecant of x. And as x goes to infinity, this denominator here goes to 0 because we've got the 1 over x, right? Sine x is bounded between 1 and negative 1, divided by something getting larger and larger, so the denominator goes to 0. The numerator is 1, so its limit is 1. So this limit is of the form 1 over 0. Is it infinity? Is it minus infinity? If you graph the function, you see that it spends a lot of time on the positive side of the x-axis and a lot of time on the negative side of the x-axis. It has all these asymptotes. And in between the asymptotes, it alternates positive, negative, positive, negative, positive, negative. But it's getting further and further away from 0. So this function really has no limit at all. It's not infinity. It's not negative infinity. It just does not plain exist. So even in the case of infinite limits, we have to be very careful about these indeterminate forms. So what's even less predictable is if you have a quotient where the numerator and the denominator both go to 0. And those are the ones that we're going to look at the most today. Here are some examples of these kinds of 0 over 0 indeterminate forms. So here's one, sine squared x over x as x goes to 0. Okay, can we just plug in x equals 0? No, because the denominator goes to 0. What happens to the numerator as x goes to 0? Well, sine x is 0 as x goes to 0. And so the numerator also approaches 0. What would be this limit then? Well, we have no limit law, which allows us to divide the 0 by 0. Instead, we have to think about things in a way which will let us get around that. So what if instead we wrote this as sine x over x times sine x? If instead of sine squared x over x, it was sine x over x times sine x. Well, what's the limit as x goes to 0 of sine x over x? That is 1. And the limit as x goes to 0 of sine x? 0. And in this case, we have a limit of each factor of that product. And so the product goes to 0. Here's a graph of sine squared x over x. And you can see the limit is 0. So here's a case where we have a 0 over 0 indeterminate form. And the answer turned out to be 0. What if we tried this one instead? X over sine squared x. What is the limit as x goes to 0 of x over sine squared x? Well, again, we have the denominator going to 0. So maybe it doesn't exist. But the numerator also goes to 0. So it's indeterminate. Break it up instead as x over sine x times 1 over sine x. What's the limit as x goes to 0 of x over sine x? That's 1, because it's the reciprocal of sine x over x. And we know that goes to 1. What's the limit as x goes to 0 of 1 over sine x? Well, it doesn't exist, right? From the right, it's infinite. From the left, it's negative infinite. So this one doesn't exist. Here's the graph. Looks like this. Goes up, and then comes down. So in the first case, 0 over 0 turned out to be 0. In the second case, 0 over 0 does not exist. And if you were to go from the right to the left, you would get 0 over 0 is infinity. 0 over 0 is negative infinity. How about this one? Sine squared x over sine of x squared. Sine squared x over sine x squared. Well, let's use a little bit of approximation to guess the value of this limit. We know when we say that the limit as whatever goes to 0 of sine of whatever over whatever is 1, what we're saying is that for a small angle, the sine and that angle are pretty much the same thing. For small x, sine x and x are about the same. Okay? So if that's true, sine squared x should be pretty close to just x squared. And also, the sine of x squared is also small, so its sine should also be close to x squared. So if you use that approximation, both the numerator and the denominator should be approximately x squared. In that case, you would guess that the limit is 1, and that's in fact what happens. So here, the limit of the function is 1. Notice that this function has lots of all kinds of vertical asymptotes. We've got one here at the square root of pi and the square root of 2 pi and so on. But near 0, it's nice and well defined, and the limit is 1. So in this case, 0 over 0 turned out to be 1. How about this one? Limit as x goes to 0 of sine 3x over x. What's the limit of the denominator? 0. What's the limit of the numerator? Also 0. Okay. But we did a bunch of examples like this way back when we did section 1.4, where we had sine of something over sine of something else. Do you remember what it was? Right. You do a little bit of an algebraic manipulation, and this is the thing that pops out. You can write this as sine 3x over 3x times 3x over sine x, and then the x and the sine x will cancel in the limit. The 3x and the sine 3x will cancel in the limit, but there's a leftover 3. The answer turns out to be 3. Here's a graph of the function, and you can see we have a limit of 3. So I gave you 4 examples of a quotient of 2 functions where in the limit the numerator went to 0 and the denominator went to 0. And I got 4 different answers. I got 0, I got 1, I got 3, and I got does not exist. If I had taken it from the right or the left, I would get plus or minus infinity. Okay? And you might notice that this limit here, if I had just changed that 3 to a 4, I could get a limit of 4. Or 17, I could get a limit of 17. So indeterminate limits can actually have any possible real number value, or they can be positive infinity, or they can be minus infinity, or they can be neither. That's how bad indeterminate limits can be, limits of indeterminate forms. All of these look like 0 over 0, but they all have different answers, which is why we have no limit law for quotients of functions if the denominator goes to 0. Okay? Now, what we're not saying is that these limits don't exist. Sometimes students will look at, say, this quotient here and say, oh, 0 over 0, that's not defined, so this limit does not exist. But that's not true. We know the limit is 3. Okay? So when we say 0 over 0 is not defined, what that's telling us is that the limit is indeterminate. And indeterminate, or indeterminate, does not mean undeterminable. It means not yet determined. Okay? So we say it is 0 over 0, but 0 over 0 isn't really anything that it can be equal to. Okay? So we're playing a little game with the word is, which is why I put, you know what this is, right? I always have to check my historical references when I'm working with students. Yes? Okay. Was Bill Clinton at the law school yesterday? Here? Bill Clinton's speaking at our commencement. Yeah. Okay. Wow. I don't know. I didn't get the memo. So okay. So remember what Bill Clinton says. It depends on what the meaning of the word is. Limits of indeterminate form may or may not exist, even though 0 over 0 is never defined. Okay. The whole thing is kind of like a tug of war. If you've got one group of Boy Scouts tugging on one side, another group of Boy Scouts tugging on the other side, then whoever's going to win depends on which side is stronger. If you have a limit of a quotient, then the numerator of that quotient is pulling things larger. The denominator of the quotient is making things smaller. And so in the limit, it depends on which one is pulling harder than the other. Okay. So I want to introduce a tool for finding some limits of indeterminate forms. And it's all based on a simple case extrapolating to a non-simple case. So here's the simple case. Suppose f and g are linear functions. Their graphs are straight lines. And we know that f of a and g of a is some point, are both 0. What should the limit as x goes to a of f of x over g of x be? Well, you know that f and g are lines, so they're nice linear functions. So their quotient is a rational function. And in most cases, to find the limit of a rational function, you just plug it in. Can we plug it in here? Well, no, we can't, because unfortunately, we're taking the limit at exactly the point where the denominator goes to 0. Okay, so we can't do that. Nor can we can't plug it in the numerator either, because that's going to 0 as well. So this is one of those indeterminate 0 over 0 forms. How will we find the limit? Well, we can't do it just by looking at it. What we have to do is think about what the equations for these functions would be. If f has a graph which is a straight line, what form does its equation take? What's the form of a linear function? mx plus b. Okay, so we know it's got a slope and an intercept. And since we know that f of a is 0, we can actually figure out what that intercept is. We can do the same thing for g. It turns out that f of x has to have a formula which looks like m times x minus a. G of x needs a formula that looks like m times x minus a. But of course, these are probably different slopes. So we'll call one of them m1 and the other one m2. Okay, so because f is a line and it goes through the point a comma 0, it has to have this equation. Ditto for g, it's a line, goes to the point a comma 0, so it has to have this equation. And the quotient of f and g is the quotient of m1 times x minus a divided by m2 times x minus a. The x minus a's cancel, and you get the ratio of the slopes. So for linear functions, the limit as x goes to a of f of x over g of x is the limit as x goes to a of one slope divided by the other slope, which doesn't depend on the fact that f of a and g of a are 0. Right? It just divides out nice and smoothly. Okay. So that would be great if all the functions we ever had to look at were lines. Unfortunately, that's not true. So, oh yes, here's a nice little picture. F of x over g of x, you can subtract f of a. You get f of x minus f of a over g of x minus g of a divided by x minus a, and you get the slope, the ratio of the slopes. Okay, now writing it in this way as f of x minus f of a, which happens to be 0, divided by x minus a, and then dividing the denominator by the same x minus a, is getting you to think about the relationship between the ratio of the functions and the ratio of their average rates of change. Okay, that's another clue. The question now is, what do we do with nonlinear functions? Well, what do we always do with nonlinear functions? If we want to find the rate of change of a function which doesn't have a constant rate of change, we approximate it and find the rate of change of that approximation. Or to say it another way, if we're trying to find the slope of a curve, we can't find the slope of a curve, so we draw the tangent line and find the slope of that tangent line. And what's the slope of the tangent line of the to the curve of a function? It's the derivative, right? So can you approximate a function at a point with a linear function? Sure, we know how to approximate functions with linear functions. You take the linear approximation, which is just another name for tangent line. The slope of that linear function is the derivative of the function at that point. So for linear functions, the ratio of indeterminate forms is very easy to figure out. For nonlinear functions, it looks like we can use the derivative somehow to find that limit. Okay, so here comes the whole story. Suppose f and g are differentiable functions, and g prime of x is not always 0 near a. So it could be 0 at a couple of points, but not always 0. Suppose that the limit of f and the limit of g are both 0, or the limit of f and the limit of g are both infinite, that is plus or minus infinity. Suppose also that the limit of the quotient of the derivatives exists, or is infinite, or negative infinite. Then the limit of the original quotient exists and is the same thing. Or I should say the limit of the quotient is the same thing. So if you have a limit of indeterminate form, and if the derivative of the numerator and the derivative of the denominator divide, and that thing has a limit, then the original limit is the same. Okay, so if this is finite and the same thing. If this is positive infinity, this is also positive infinity. If this is negative infinity, this is also negative infinity. Which is kind of cool, because many times taking the derivative of a function will make it simpler, and the simpleness of it will help us find that actual limit. Okay? So this is known as L'Hopital's rule. Now, not to scare you with the French, but this is Guillaume François Antoine Marquis de L'Hopital, which just means Bill, Frank, Tony, Duke of the Hospital. So he wanted to be an army man, but he couldn't see very well. So instead, he had to go into math. I know that lots of people were forced into math by bad eyesight. And he solved a famous problem called the brachistochrone problem. What is a brachistochrone? Well, picture a bowl, and then picture taking a marble and letting it roll off the side of the bowl down to the bottom of the bowl. Okay? Now, depending on where you start that ball, whether you start it right at the top of the bowl, or maybe in the middle of the bowl up around the edge, or towards the bottom of the bowl, you can measure the time it takes to get to the bottom. For the special shape known as the brachistochrone, it will take the same amount of time to get to the bottom no matter where you start it. Whether you started from the bottom or whether you started from the top, it will take the same amount of time to roll to the bottom. Now, who cares about something like that? Well, you could use such a bowl to tell time, because you could let the ball roll back and forth, and it would always cross the bottom at the same time interval. So he solved that problem. But he wasn't the world's greatest mathematician. He did have a lot of money, though, and he patronized many other mathematicians, among them Johann Bernoulli. Bernoullis were a whole family of prolific mathematicians, and this guy Johann was on the L'Hopital gravy train. And Bernoulli is the one who proved this theorem for the first time, and in deference to his patron, he named the theorem after L'Hopital. Okay, so it's L'Hopital's rule, but it's actually Bernoulli's theorem. Okay, how does this actually help us find limits of indeterminate forms? Well, let's look at this one, which we saw already, and we had to solve by some creative factoring. Let's look at the limit as x goes to 0 of sine squared x over x. Well, the numerator goes to 0, denominator goes to 0. This limit is indeterminate. To try L'Hopital's rule, we want to take the derivative of the numerator and the derivative of the denominator. Okay, now the h here is my funny decoration just for saying that this equality is contingent on L'Hopital's rule. I'm using L'Hopital's rule here. And so, it's only going to work if where I end up is an answer to the limit. Okay, so the derivative of sine squared x, pull down the 2, take the derivative of sine x, get 2 sine x cosine x. The derivative of x is 1. What does this quotient go to? Well, the 2 over 1 is not going to be a problem. Cosine x, what's the limit of cosine x as x goes to 0? 1. And the limit as x goes to 0 of sine x is 0. So this limit is 0 because the sine x goes to 0. All right, so thanks to L'Hopital's rule, we know that the original limit is 0 as well. Okay? So which way do you like better? Do you like this L'Hopital's rule way, or do you like the factorization and take the limit of each factor way that we did the first time? How many prefer L'Hopital's rule? Okay, see, like I said, it's a very powerful tool to find these limits of indeterminate forms. Let's try it for sine squared x over sine x squared. Numerator goes to 0, denominator goes to 0. If we're lucky, we can use L'Hopital's rule to find the limit. For that, we would need the derivative of the numerator and the derivative of the denominator. The derivative of the numerator is, numerator and denominator both go to 0. The derivative of the numerator is 2 sine x cosine x. The derivative of the denominator is cosine x squared times 2x. Both of those are by the chain rule. Okay. And what now? Well, what's the limit of the denominator now? The limit of the denominator? The limit of the denominator is still 0, along with the limit of the numerator. Okay? So did we get anywhere? Well, we didn't get to the answer yet, but we did take one derivative. And we're still indeterminate. So why don't we try to take the derivatives again? Again, try L'Hopital's rule. Again, we'll take the derivative of the numerator and the derivative of the denominator. The derivatives are slightly more complicated because they're going to need the product rule. But the derivative you get in the numerator is cosine squared x minus sine squared x. And the one you get in the denominator is cosine x squared minus 2x squared sine x squared. Now, what does the denominator go to? The denominator goes to 1 because cosine of 0 is 1, and all this stuff goes to 0. The numerator, this goes to 0, and this goes to what? 1. Okay, numerator and denominator both go to 1, and so the limit I get is 1. Okay, so because this goes to 1, this goes to 1, the quotient goes to 1. Because this limit exists and is the same thing. Because this limit exists and is the same thing. And so my original limit is, in fact, 1. Okay. Okay, so I get a limit of 1. Any questions about that process? Yes? This part right here? Okay. Remember that cosine of 0 is 1. So the denominator goes to 1 minus 0 times 0. The numerator goes to 1 minus 0. Oh, I got... Oh, okay. So it's just the... I'm again using L'Hopital's rule. So I'm again trying to take the derivative of the numerator and the derivative of the denominator, and that's going to use the product rule. For the product rule, I take the derivative of sine, which is cosine, multiply it by cosine. That gives me the cosine squared x term. Then I'll take the sine by itself, multiply by the derivative of cosine, which is minus sine. That gives me the minus sine squared x term. Okay? This one is also quotient rule, I mean product rule, because the derivative of x is 1, multiplied by cosine x squared. leave the x by itself, multiply by the derivative of cosine x squared, which is negative sine x squared times 2x. So you end up with a minus 2x squared sine x squared. Okay? So since this limit exists, and therefore this limit exists, everything has a limit of 1. Okay, so do you still like this method better, even though you had to do a little bit nasty differentiation twice? Uh-huh. You are not supposed to use the quotient rule. That's correct. Notice in the statement of L'Hopital's rule, we are not taking the derivative of the quotient. We are taking the quotient of the derivatives. And as we know from the quotient rule, these are not the same thing. Okay, so this is the time when it's okay to take the quotient of the derivatives. That's a good question. I wanted to bring up that point, and you brought it up for me. Okay. Any other questions about this example here? Okay. How about sine 3x over x? We know the answer, and we know the one way to do it is through creative factoring, or multiplying and dividing by the same thing. Using L'Hopital's rule, though, you can take the derivative of sine 3x. It's 3 cosine 3x. The derivative of sine x is cosine x. Okay, and now the numerator goes to 3, the denominator goes to 1, so the quotient goes to 3. Pretty sweet, right? The indeterminacy is differentiated out. Uh-huh.
If you don't get like a number by the second derivative, you could like just say like you can't get the DNT first.
As a rule of thumb, if you don't get a limit by the time you take 2 derivatives, okay, so I guess in terms of test-taking strategies, if you take 2 derivatives and you don't get a limit, you might think that you may have done the wrong thing. But mathematically, certainly not. I mean, there could be any number of steps to L'Hopital's rule which would not give you an answer until the end. Right? Just remember, indeterminate is not a final answer. It means I don't know. I don't know yet. Okay, and so it might be that further differentiations will get you to the answer. Now, how would you know if you were going towards the right answer or off in the wrong direction? Remember what I said earlier about sine x being pretty close to x? And this is pretty close to x squared, and this is pretty close to x squared in a different way. Okay? So the fact that this is close to x squared and this is close to x squared tells you that 2 derivatives are going to bring it down to a ratio of constants. Because if you just had x squared over x squared, it would go x squared over x squared, 2x over 2x, still indeterminate. 2 over 2, not indeterminate. And that's what's happening here. X squared over x squared, indeterminate. 2x, see the 2 x's, over 2x, indeterminate. And then 2 over 2, not indeterminate. Okay? So this one, we got 3. Okay. Here's another one. Try this one. Okay. So you took 2 derivatives. Okay. Any other answers? Okay. So he must be right because he answered first. Huh? All right. So the answer is 0, but not for the reason he gave. And why is that? What's the limit of the numerator? What's the limit of the denominator? 1. Okay? So L'Hopital's rule does not apply in this case. The answer is 0 because it's not an indeterminate form. Okay? If you take the derivative of the numerator, you get 1, and the derivative of the denominator, you get minus sine x. And the limit of that would be minus infinity. Okay? So if you got minus infinity, you use L'Hopital's rule, and that would not be the right answer. If you again try L'Hopital's rule on this other non-indeterminate limit, then you do coincidentally get back to the right answer. So 2 wrongs make a right, I guess. Okay? But beware, if you're examining a limit, then, and you want to use L'Hopital's rule, you have to make sure that it is actually a 0 over 0 indeterminate form. Otherwise, you will get the wrong answer. Unless you do it twice. You might get the right answer. Okay, and this is what I was trying to say when I said it's an important tool, but it has to be used in the right situations. Okay. So next I want to talk about relative rates of growth. And what this means is comparing how fast functions grow. There are different ways that certain things can grow, and certain functions which grow faster than others. Why would you care about these things? Well, maybe you have a way to, say, break some kind of code. Then that would be a bad thing because someone could write a program to do that algorithm and break your code. But if you were able to show that the amount of time it would take to break your code is longer than the amount of time before the sun goes supernova, then that code is effectively unbreakable. Okay? And this is how cryptology works. There is a way to break any code. It just takes so much time and so much computing power that it's effectively unbreakable. Okay? And so relative rates of growth is one way to describe how long something takes or how fast something grows. And comparing relative rates of growth means looking at quotients of functions which go to infinity and deciding what the quotient actually goes to. So here's an example. Maybe we've got one algorithm which, if x is the number of bits in the problem, takes this much memory to solve, 5x squared plus 3x minus 1. And another algorithm which takes 3x squared plus 7x plus 27 bits of memory. And then you let x go to infinity and figure out what the quotient is to determine if either one of these is better than the other. Okay, well, what is this limit? Actually, we know the answer to this because we learned some techniques from chapter 1 to answer it. So what's the limit here? 5/3. Is there a way to do this using L'Hopital's rule? L'Hopital's rule works for infinite over infinite limits as well. So let's do it. Limit as x goes to infinity, 5x squared plus 3x minus 1 over 3x squared plus 7x plus 27. Take the derivative of the numerator and denominator. We get 10x plus 3 over 6x plus 7. Still infinity over infinity, right? Numerator still goes to infinity. Denominator still goes to infinity. But as you can see, we went from a degree 2 polynomial to a degree 1 polynomial, and a degree 2 to a degree 1. So we did get simpler. Okay, and that leads us to believe that maybe one or a few more differentiations will get us there. And in fact, it does. The derivative of 10x plus 3 is 10. The derivative of 6x plus 7 is 6. And the quotient is 5/3. Okay, so this is another justification of this rule that we had, where if you have a limit of a rational function and the degree of the numerator and the degree of the denominator were the same, then you could just look at the quotient of the coefficients of that highest degree term. So that's reassuring, right? You can also look at limits of quotients where the degrees are different in the numerator and denominator. Okay, if you remember the rule of thumb, then we know what this limit is actually going to be. And let's see how L'Hopital's rule shows it. Limit as x goes to infinity, 5x squared plus 3x minus 1 over 7x plus 27. The derivative of the numerator is 10x plus 3. The derivative of the denominator is 7. And now this limit is no longer indeterminate because the numerator goes to infinity, the denominator is 7. So the limit is infinity. Okay? Once you get to a situation where it's no longer indeterminate, then you cannot use L'Hopital's rule anymore. You just have to evaluate the limit of the numerator and the denominator. Okay? And dividing by 7 is the same as multiplying by 1/7. This is like saying 1/7 times a function which goes to infinity. Okay. How about this one? 4x plus 7 over 3x squared plus 7x plus 27. Again, this is indeterminate because the numerator and denominator both go to infinity. So again, we can try L'Hopital's rule. The derivative of the numerator is 4. The derivative of the denominator is 6x plus 7. And this is no longer indeterminate because the numerator goes to 4 and the denominator goes to infinity, so the quotient goes to 0. Okay. So this is pretty generic, right? It's not depending too much on the coefficients of these polynomials. What it's really just looking at is the degree of the numerator versus the degree of the denominator. So that shows us that anytime you have a rational function, a quotient of polynomials, where the degree of the numerator is p and the degree of the denominator is q. If p is greater than q, then the limit is infinity. I guess I should say plus or minus infinity, depending on what the coefficient of the top degree term on f is. If p is less than q, then the quotient goes to 0. And if p is equal to q, then the limit of the quotient is the ratio of the leading coefficients of f and g, the degree p coefficient of f and the degree p coefficient of g. Okay, so we had said this before using a funny algebra technique where we factor out the largest power of x from the numerator and the denominator. We get a bunch of zeros and we can cross it all out. But this way, through L'Hopital's rule, is slightly cleaner. Okay, questions about that? Okay, good. Well, we can use this not just for quotients of polynomials, but say comparing exponential growth to geometric growth. So let's take a look at the limit as x goes to infinity of e to the x over x squared. The numerator goes to infinity. The denominator goes to infinity. So this is a situation where we could have tried to apply L'Hopital's rule. So go ahead and try that and tell me what answer you get. Okay, does anyone have an answer? By the way, am I amplified in the back? Okay, good. Yeah. E to the x over 2. So by that you mean the limit as x goes to infinity of e to the x over 2. And what is that limit? Infinity. Right. So e to the x goes to infinity, x squared goes to infinity. So we can try L'Hopital's rule. L'Hopital gives us the limit as x goes to infinity, e to the x over 2x. Still indeterminate, right? Still infinity over infinity, but closer than we were before, because we went down from x squared to 2x. Okay, L'Hopital again, e to the x over 2, but we want the limit of that would be infinity. So the original limit, the limit as x goes to infinity, e to the x over x squared, is infinity. What that means is that if you have one function which grows exponentially and one function that grows like the square, then that exponential function is going to get bigger faster than the x squared function. If you were to plot these two things, plot e to the x and x squared, both of them go to infinity, but e to the x grows much, much faster. Okay, so let's try it with limit as x goes to infinity, e to the x over x cubed. Yes? Infinity. Okay, you're going to short circuit my little exercise here. Why do you say infinity? Okay, so something like this. I take the derivative e to the x over x cubed, differentiate the numerator and denominator. You would get e to the x over 3x squared. Still indeterminate limit, right? But simpler denominator than before. So take another derivative, e to the x over 6x. Still indeterminate because both go to infinity. So take another derivative, e to the x over 6. No longer indeterminate. Now we can determine that the limit is infinity. So x cubed grows faster than x squared, but e to the x grows faster than both of these. Okay, so now you might see that the general pattern is not so much related to the power here, but the fact that this is some power function, and that differentiating it makes it a smaller power function. So how about this one, e to the x over the square root of x? How are those homework envelopes doing? Who's got them? Okay. Does anyone still have homework to turn in? Okay, well, if you forgot, I'll keep them up here at the end. You've got mail. Okay, so if we try the same thing we did before, what we noticed is in the x cubed case, take enough derivatives and you get worked down to a finite constant here, just 6. That doesn't work here because if you take the derivative of that denominator function, x to the 1/2, you get x to the minus 1/2. Take another derivative, you'll get x to the minus 3/2. So we don't get to work it down to a constant. But maybe we don't even have to use L'Hopital's rule at all, because remember, x to the 1/2 is less than x to the 1, at least if x is bigger than 1. The square root of x is usually less than x, and so e to the x over the square root of x is greater than e to the x over x, and we already showed that the limit of this thing on the right is infinity. Okay, so if a function is larger than a function with an infinite limit, well, then it has to have an infinite limit too. So you wouldn't even need L'Hopital's rule to show that this limit is infinity. Or, if you must use L'Hopital's rule, you can. E to the x over the square root of x, take the derivative of the numerator, you get e to the x. Take the derivative of the denominator, you get 1/2 x to the minus 1/2. And now write it as a single, write it without fractions. You can write it as 2 times the square root of x times e to the x. And now this is no longer indeterminate. Both the square root of x and e to the x go to infinity. So the product this time goes to infinity. Okay, so you can use L'Hopital's rule, but you don't have to. If you do use it, then you end up with something that's infinity times infinity, which is not indeterminate. Okay, well, let's be a little bit general then. The general theorem is that if you have any positive number, not just a positive whole number such as 1, 2, or 3, but a positive fraction will work too, or a positive irrational number if you really want to get crazy. But the quotient of e to the x by x to the r will have an infinite limit. So exponential growth dominates any power law growth that you can write down. Okay, so that's kind of cool. It's a nice general fact. And it's one reason that we talk about exponential growth being so fast. It's faster than any polynomial or any algebraic growth. And how would you show that? Well, we showed it for r equals 2 and r equals 3 by taking derivatives until we worked it down to a constant. So if this were 3, you go e to the x over x cubed, compared to the limit of e to the x over 3x squared, compare that to the limit of e to the x over 6x, compare that to the limit of e to the x over 6, and that limit is infinite. If you had x to the 4th, you would just do one more derivative, right? You go from x to the 4th, 4x cubed, 12x squared, 24x, and 24. The constant that you get, if you take x to the r, where r is a positive whole number, and differentiate it r times, is known as the factorial of r. And we write it with this exclamation point. If I had a voice today, I would do a little joke where I shout out r factorial, but I can't. So just picture that joke, and you can laugh now anyway. Thank you. All right, so if it were 3, then you get 3 times 2 times 1, which is 3 factorial, or 6. If it were x to the 4th, you get 4 times 3 times 2 times 1, which is 24. We write that as 4 factorial. 10 factorial is some other large number. But eventually, it's e to the x over a constant, which goes to infinity. Now, what if r is not a whole number? Then you can do something like we did before. Compare e to the x over x to the r with e to the x over x to the m, where m is the next smallest positive whole number. So say you had r was 3.5, then e to the x over x to the 3.5 would be greater than e to the x over x to the 4. And by the previous steps, that one would have an infinite limit. Okay? So I took those cases I did before and sort of generalized them, which is kind of nice. So even more general, you can say that any exponential function beats out any power function, not just e to the x, but a to the x when a is any base which is bigger than 1. The difference being that if you have a to the x over x to the r, and you take the derivative of the numerator a to the x, you don't get a to the x, you get a to the x times a constant natural log of a. Well, if you take r derivatives, you get r factors of this constant natural log of a to the r power. But that's still going to be some constant, and the a to the x limit of infinity is still going to determine that the entire quotient has a limit of infinity. So even if you did something radical, like take the limit as x goes to infinity of 1.000000001 to the x, that's going to grow very slowly, but eventually become infinite. Compare that to x to the, how many zeros do I have here? X to the billion. That limit will still be infinity, even though it's going to take a very long time before the numerator is even larger than the denominator. Okay? Any exponential function, regardless of the base, will grow faster eventually than any power function, regardless of the power. That's a nice general fact to know. Okay. Logarithmic functions are sort of on the opposite side. If you compare any power function to any logarithmic function, then it's the logarithmic function which grows slower than the power function. So natural log of x grows slower than x to the 1/2. It grows slower than x to the 1/10. It grows slower than x to the 0.1. No matter what power function you compare, logarithm is slower than it. And the reason for that is that we can use L'Hopital's rule. Natural log of x becomes 1 over x. X to the r becomes r times x to the r minus 1. And then we can write this without a compound fraction, right? We can write it as 1 over x to the r with another constant r in the denominator. And so the limit of this quotient is, well, it's a finite number divided by something going larger and larger. The limit would be 0. Okay, so that's another kind of cool fact. Exponential growth dominates any power, and any power dominates logarithmic growth. So if you're a computer scientist, you like algorithms which grow in logarithmic time, because that's about as slow as it can get. Or it's still going to grow to infinity, but slower than anything else. Actually, there are some algorithms which grow like the logarithm of the time, which is even better. Okay, but enough about rates of growth. Let's look at some of the other indeterminate limits that we know of and see how to solve them. Let's find the limit as x goes to 0 from the positive side of the square root of x times the natural log of x. Now let's remind ourselves what these limits of these factors actually are. As x goes to 0, square root of x goes to 0. As x goes to 0, natural log of x goes to minus infinity. X has to go to 0 from the right, because natural log isn't defined for negative numbers. But as x goes to 0 from the right, then the limit is minus infinity. So this quotient, this is a limit of a product where one factor goes to 0 and the other factor goes to minus infinity. Think about the ambivalence there in 0 times infinity. 0 times anything would be 0, so maybe this limit is 0. On the other hand, if you take a number times something which is really, really, really large, chances are you get something really, really large, so maybe the limit should be infinity. So the answer is going to depend on how fast one of them is going to 0 compared to the quickness by which the other one goes to infinity. So let's figure this out. To use L'Hopital's rule, though, we would have to try to make this into a quotient. So what I'll do is rewrite the square root of x times natural log of x as natural log of x divided by 1 over the square root of x. Why would I do that? For one reason only, because I can use L'Hopital's rule on quotients. In no other way would we want to write the limit this way, right? But in this case, because L'Hopital's rule works on quotients, I can jury-rig the expression to make it look like that. Okay, well, let's check. As x goes to 0, numerator goes to minus infinity. Denominator goes to plus infinity. The denominator is 1 over the square root of x. As the square root of x gets smaller and smaller, 1 over it gets larger and larger. So plus infinity over minus infinity. Actually, I have it backwards. Minus infinity over plus infinity. That is an indeterminate limit. So I can try L'Hopital's rule. The derivative of x, natural log of x is 1 over x, which I've written here as x to the minus 1. It's the same thing. The derivative of 1 over the square root of x is the derivative of x to the minus 1/2, which is minus 1/2 x to the minus 3/2. Now, it's very strange to write a quotient of two power functions with negative powers like that. It would be easier just to write it as a single function. X to the minus 1 divided by x to the minus 3/2, you're going to subtract these powers, right? Minus 1 minus negative 3/2 is positive 1/2. And so the actual limit I have is negative 2 times the square root of x. As x goes to 0, what happens to negative 2 times the square root of x? It goes to the square root of 0, which is 0. Okay, so in this case, this product goes to 0, even though one of them is going to 0 and the other one's going to minus infinity. Any questions about that? Okay. Well, then let's try an indeterminate difference. Let's look at the limit as x goes to 0 from the right-hand side of 1 over x minus the cotangent of 2x. We know that as x goes to 0 from the right, 1 over x goes to infinity. As x goes to 0 from the right, cotangent of x goes to infinity as well, because cotangent is cosine over sine. And sine is going to 0, cosine is going to 1, so the quotient is going to go to plus or minus infinity. In this case, it goes to plus infinity. So we're just subtracting something which goes to infinity from something else which also goes to infinity. What should the difference of these infinities be? And you can imagine that's going to depend on how fast one thing goes to infinity versus the other thing going to infinity. Maybe they're exactly going to infinity at the same rate, then they would cancel out. Maybe one's going to infinity faster, then that would make the difference go to plus or minus infinity. So, well, enough waffling. Let's try to actually figure it out. The only way to really figure it out using L'Hopital's rule is to rewrite your indeterminate form as an indeterminate quotient. So when I have two fractions, this is cosine over sine, I can combine them to make a quotient. So 1 over x minus cotangent of 2x is 1 over x minus cosine over sine, cosine of 2x over sine of 2x. And then add those fractions to get sine 2x minus x times cosine 2x over x times sine of 2x. Did you wince there? One minus x cotangent of 2x over x. You could do it that way too. Yeah. Yeah, well, we're still going to have to take derivatives, right? Okay. So in this case, I have to take the derivative of sine of 2x minus x times cosine 2x. And I have to take the derivative of x times sine of 2x. Both of those are going to use the product rule. So by L'Hopital's rule, if this limit exists, then this limit exists. And this is cosine 2x plus 2x sine 2x over 2x cosine 2x plus sine 2x. So what does the numerator go to? Numerator goes to 1, because this term goes to 1, and this goes to 0. What does the denominator go to? Denominator goes to 0 because this x here is going to make that term go to 0, and sine of 2x is also 0. So our limit is of the form 1 over 0, which is kind of indeterminate, but not the kind of indeterminate that we can use another L'Hopital's rule on. Instead, we have to think about this denominator as x goes to 0 from the right. Is it positive or negative? It's positive, because x is positive. Cosine will be positive. It's hovering around 1. Sine of x is also going to be positive. So the numerator is close to 1. The denominator is close to 0, but is positive. So the quotient is going to go to positive infinity. Okay? The numerator tends to 1, the denominator tends to 0, but the denominator is always positive if x is positive. So the limit is going to be positive infinity. I guess from the left-hand side, we would get negative infinity. Yeah. Okay, so the method you described would still require one derivative. Your derivatives would be a little bit simpler. That's true. All right. So here's another way to think about this. And you draw a big thought cloud over this, because this is not something that we can write for homework, but it does help us understand or predict what these answers are going to be. So remember that sine of anything over that thing goes to 1 as that thing goes to 0. And the same thing is true for tangent. Tangent of 2x over 2x goes to 1 as x goes to 0. So if 2x is small, tangent 2x and 2x are about the same thing. So 1 over x minus cotangent 2x is a lot like 1 over x minus 1 over 2x, because cotangent is 1 over tangent, and tangent of 2x is approximately x. So 1 over 2x minus 1 over x minus 1 over 2x is equal to 1 over 2x, and that definitely goes to infinity as x goes to 0 from the positive side. So you can use L'Hopital's rule to justify it, but to intuit it, you can sometimes use approximations to guess the answer. All right? That's helpful if you have this big limit and you're like, what am I supposed to do here? You can use approximations to guess the limit before you dive into the actual justification. There's a two-step process, right? First you think it, then you do it. Okay. Let's look now at indeterminate powers. Find the limit as x goes to 0 from the positive side, 1 minus 2x to the 1 over x. All right, why is this thing indeterminate? Well, what happens to the base there, 1 minus 2x, as x goes to 0? What is the base approach? Base approach is 1, and 1 to any power is 1. So in this case, maybe the limit should be 1. On the other hand, what does the power approach as x goes to 0 from the right-hand side? The exponent there. The exponent is 1 over x as x goes to 0. What do we get? We get infinity. So this is an indeterminate limit. It's of the form 1 to the infinity. Take anything that's close to 1, raise it to a larger and larger power. If it's greater than 1, you'll get infinity. If it's less than 1, you'll get 0. So 1 to the infinity is indeterminate. To resolve this indeterminate limit, we need to convert it to something we can use L'Hopital's rule on. So what we'll do is we'll take the logarithm. Okay, because the logarithm is what undoes a power function. If this limit exists, the logarithm of the limit will be the limit of the logarithm, and the logarithm of the power is the exponent times the log of the base. Now that I can write as natural log of 1 minus 2x over x. As x goes to 0, the denominator goes to 0. As x goes to 0, the base goes to 1. And what's the natural log of 1? Natural log of 1 is 0. E to the 1 is e. All right. Natural log of 1 is 0, which is good news because we are in a 0 over 0 indeterminate limit. And I know what to do with those. I'm going to whack this with the sledgehammer of L'Hopital's rule, right? So I want the derivative of the numerator and the derivative of the denominator. The derivative of 1 minus 2x is negative 2 over 1 minus 2x. Why the negative 2? 2 words. Chain rule. Right, because the derivative of 1 minus 2x is minus 2. The derivative of x is 1. And now it's no longer indeterminate because the numerator goes to negative 2 and the denominator is 1. So the limit here is negative 2. Pretty cool, right? Take the log, use L'Hopital's rule on the log, and you get the limit. However, this is not the answer to the question that was asked. This is the logarithm of the answer to the question that was asked. So how do I convert this back into the answer to the actual question? How do I undo the natural log? Right, raise to the e power. Well, raise the e to that power. So what I want is e to the minus 2. Okay, so not too tricky. except for the part where you have to remember to answer the actual question asked. So if you end up computing the natural log of the limit, to get the correct answer, you want to raise that limit, put e to that limit, or that power. Okay, here's another one here. Limit as x goes to 0 of 3x to the 4x. 3x goes to 0, 4x goes to 0. 0 to any power is 0, unless the power is 0. And anything to the 0 power is what? 1. So here we have a power which to some way is pulled to 0, and to another way is pulled to 1. What should the limit be? Well, again, we'll try this. Take the log and use L'Hopital's rule. Okay, why don't you try this one? It might take you maybe 2 or 3 minutes, but the process is the same as the one before. Take the log and use L'Hopital's rule to find the limit of the log. Feel free to check with your neighbor if you're still sweating this out. Okay, so I'm ready for a volunteer. Does anyone have an answer? You guys get an answer? Got one? What'd you get? E to the 4/3. Okay. Any other answers? E to the 4/3, that sounds pretty specific. That might be the right answer. Let's see. Okay, remember that we need to take the log first. Okay, so the log of the limit is the limit of the log, we hope, as long as that limit exists. And the log of 3x to the 4x is 4x times the log of 3x. And this is an indeterminate product, because this goes to 0, this goes to minus infinity. So we convert that indeterminate product into an indeterminate quotient, making it log 3x over 1 over 4x. We could also make it as 4x divided by 1 over log of 3x, But I would rather differentiate the log of 3x than I would 1 over the log of 3x. So usually easier to write it that way. The derivative of the log of 3x is 3 over 3x. The 3 comes out by the chain rule, so you just get 1 over x. The denominator, the derivative, is negative 1 over 4x squared. That's the power rule in disguise. You could also use the quotient rule. So I get the limit as x goes to 0 of, well, let's see, the 4x squared and the 3x here. We can divide those, and we get negative 4x. And that limit is 0. Are we done? No, we're not done. We wanted the log of that answer. But that's the log of the answer that we wanted. So our original answer is e to the power of the answer we just got. Right? So e to the 0 is 1. Does that make sense? So if you missed this squared here, and you missed the 3 that comes out from the chain rule, then you could get, that's how you would get the 4/3 here, and a limit of 4/3 in an answer of e to the 4/3. But if you take the right derivatives, you'll get a limit of 0. The fine answer would be 1. This one here, why is this indeterminate? 4x is going to 0, but the log of 3x is going to negative infinity. Why? If you look at the graph of log, you'll see that. It's basically because log is the inverse of the exponential function, and because x goes to minus infinity, log x goes to, e to the x goes to 0. So the logarithm is going to have a reflection of that. It's just true. Go back and review section 3.2, and you'll remember that. Okay? All right, so to summarize, these are basically all of the different indeterminate limit forms that you were encountering. You might have a 0 over 0 or infinity over infinity, and on those you can just apply L'Hopital's rule to the quotient. Anything else, you have to get it into an indeterminate quotient. So if you have 0 over times 0, you can rewrite it as a quotient where the limit will be 0 over 0 or infinity over infinity, and then you can proceed as before, do L'Hopital's rule. If it's infinity minus infinity, you need to combine these two pieces here to make it a quotient. Then you can use L'Hopital's rule. If it's one of the indeterminate powers, that's 0 to the 0, infinity to the 0, or 1 to the infinity, then take the natural log. The natural log of that expression will be an indeterminate product, so you can jiggle the product to make it a quotient. So those are all the tricks of L'Hopital's rule. Remember, it only works on indeterminate quotients, but most of the time you can rewrite indeterminate functions involving indeterminate quotients. And you cannot use it on non-indeterminate quotients. You will get the wrong answer. The other thing to remember is that there is money in math. You just have to name all your theorems after the guy who gave you all the money.